So, when most of us think about electricity, the big names that pop up are usually Edison, maybe Tesla.
Right, those are the household names.
Exactly. But today, we're doing a deep dive into someone often sort of left in the shadows, but absolutely crucial, Michael Faraday.
Yeah, often called the father of electricity. And his story, it's just incredible. Shows genius can come from anywhere.
It really does. Our mission today, then, is to explore this amazing journey. A self-taught scientist starts out in poverty and just revolutionizes how we understand the physical world.
And really shapes the technology we all use, literally every day.
We'll dig into his big discoveries, his really unique way of bringing science to the public, and also the sort of personal beliefs that guided him.
And we've looked at quite a bit, biographies, scientific papers, even some rarer archival stuff to piece together his world.
So where does it start? I mean, the beginning is quite something.
It really is. Imagine this young kid, practically zero formal schooling, ends up apprenticed to a bookbinder. He's just 14.
A bookbinder.
Okay. Yeah. But that seemingly, humble job, that's where his curiosity just exploded. He read everything he could get his hands on,
Everything that came through the shop.
pretty much,
Mm.
including this one really key article on electricity in the Encyclopedia Britannica. That was it. That sort of lit the fuse.
It's just wild thinking about those beginnings. Born in Newington Butts, London, 1791. His dad was a blacksmith, often sick. Family was poor.
Very poor. He was the third of four kids and apparently often went hungry. It makes his rise even more astounding.
So how did he make the jump from bookbinding to, well, science?
Well, the big turning point came when he was about 20. Finished his apprenticeship. He managed to get tickets to attend 4 lectures by the big chemist of the day, Humphrey Davy.
At the Royal Institution, right.
Exactly. And Faraday didn't just listen. He took meticulous notes, like 300 pages of them.
300 pages, wow.
Yeah. And then he didn't just keep them. He bound them beautifully.
Mhm.
Remember, he was a bookbinder, and sent them straight to Davy.
Seriously, asking for a job.
Yep, bold move. But Davy, who was also kind of self-made in science, was apparently really impressed.
I bet. By the sheer diligence, the detail.
Right. So in 1813, Davy hires him as his chemical assistant.
Hmm.
And that's the start of, get this, a 54-year career at the Royal Institution.
54 years. Incredible. So what was he doing initially? Assisting Davy with chemistry?
Exactly. Dove into chemistry. Faraday helped Davy study chlorine. He actually discovered some new compounds himself, carbon and chlorine ones.
Okay.
He also did some really early important experiments on how gases diffuse. And he was the first person to liquefy certain gases like chlorine and ammonia just by using pressure.
Liquefying gases. That
But-
sounds fundamental.
It was. And you know that cooling effect you get when ammonia evaporates, like in old refrigerators?
Yeah.
Faraday noted that. That principle is, well, basically how modern refrigeration started.
No way. So from studying gases to the fridge in my kitchen.
Kind of, yeah,
Yeah.
the fundamental principle.
Hmm.
He also isolated benzene in 1825 and even invented an early version of the Bunsen burner. Super practical, too.
So he had this knack for both deep science and, like, practical tools.
Absolutely. And that chemistry background really set the stage for what came next. The big shift towards electricity started around 1820.
Okay, what happened then?
Well, a Danish physicist, Hans Christian Kjersten, made a huge discovery. He found that an electric current creates a magnetic field.
Ah, the link between electricity and magnetism.
Exactly. And that just set the scientific world buzzing. Faraday was discussing it with colleagues, thinking about it, and he just felt, he had to push it further.
He wasn't satisfied with just knowing there was a link.
Not at all.
Yeah.
He wanted to see if electricity could do something with magnetism.
Mm.
Could it create continuous motion?
And did he manage it?
He did. In 1821, it was brilliant, really. He built this simple device, basically a wire-carrying current dangling in mercury, and it spun continuously around a magnet.
First electric motor.
Pretty much. The first homopolar motor, the very first time electrical energy was turned directly into continuous mechanical energy. It's the ancestor of, well, every electric motor since.
That is foundational. Just wow.
It was huge. Though, apparently his first paper on it caused a bit of a stir because he maybe didn't fully credit all the discussions he'd had, but the discovery itself was massive.
Okay, so that's motors. But his most famous work is maybe induction, right?
Ah, yes, electromagnetic induction. That came about a decade later, 1831. This is probably his most celebrated experiment.
The one with the iron ring.
That's the one. He took an iron ring, wrapped two separate insulated coils of wire around it.
Okay.
Then he connected a battery to one coil. And here's the magic. When he connected or disconnected the battery, he saw a tiny momentary surge of current in the second coil.
Even though they weren't touching or connected to the same
Yes,
battery.
that's mutual induction. But then he went further. He showed you didn't even need the ring or two coils like that, just moving a magnet in and out of a single loop of wire-generated current.
Or moving the wire over the
Oh,
magnet.
moving the wire, right.
Yeah.
Either way, relative motion produced electricity.
So the profound insight here, the really big deal, is that it's not just magnetism itself, but a changing magnetic field that creates an electric field, an electric current.
Precisely. That is the absolute key takeaway. A changing magnetic field produces an electric field. It sounds simple now, maybe, but it was revolutionary.
And that relationship, that's what James Clerk Maxwell later put into mathematical form, right? But one of his famous equations.
Exactly. The Maxwell-Faraday equation. It's one of the four pillars of classical electromagnetism. It explains how transformers work, how generators work, inductors. I mean, so much of our technology relies on that very principle.
It's just staggering. My phone charging wirelessly right now, the power grid, it all comes back to that 1831 experiment.
It really does. And Faraday, being Faraday, didn't just stop at the principle. He built on it. In 1832, he created the Faraday disk.
What was that?
It was basically the world's first electromagnetic generator. He rotated a copper disc between the poles of a horseshoe magnet, and it produced a steady, direct current.
So he showed how to turn magnetism into electricity and then built the first machine to do it continuously.
That's right. The ancestor of modern dynamos, the starting point for large-scale power generation.
Okay, so he's figured out motors and generators. What else? He kept going, right?
Yeah. He then turned back to chemistry, but with his new electrical knowledge. This led to his laws of electrolysis around 1832 to 1834.
Electrolysis, like using electricity to cause chemical reactions.
Exactly. He figured out the precise mathematical relationship between the amount of electricity used and the amount of chemical change produced. Super important for electrochemistry.
And didn't he also come up with some of the basic terms we use?
He did. He popularized terms like ion, electrode, cathode, anode, words we just use all the time in chemistry and physics now. He needed the language to describe what he was seeing.
Amazing. Okay, so electrochemistry, then what?
Then he started thinking about static electricity, how charges behave on surfaces. This led to another incredibly practical discovery in 1836, the Faraday cage.
Ah, the Faraday cage. I've heard of that.
Right. He showed that if you have a conductor, any excess electrical charge sits only on the outside surface. It doesn't penetrate inside.
So anything inside is shielded.
Exactly. He demonstrated it famously with his ice pail experiment in 1843. But the principle is everywhere.
Like my car during a thunderstorm.
Yep. The metal body acts as the Faraday cage, protecting you inside. Same with an airplane, even the mesh screen on your microwave oven door.
That's a Faraday cage to keep the microwaves in.
Precisely. Keeps the radiation contained. It's a simple idea with huge safety implications.
Okay, this guy's range is just incredible. What about light? Did he connect electricity and magnetism to light?
He did. That was another major breakthrough. In 1845, he found the first experimental proof that light and electromagnetism were related.
How did he show that?
He showed that a strong magnetic field could actually rotate the plane of polarization of a beam of light passing through certain materials. It's called the Faraday effect.
Rotating light with a magnet. That sounds weirdly futuristic even now.
Doesn't it? It was the first concrete link. It strongly suggested light itself had an electromagnetic nature, which Maxwell later proved mathematically that light is an electromagnetic wave. Faraday provided that crucial first experimental step.
Wow. And he wasn't done in 1845, was he?
Not quite. Same year, he also showed that all matter is affected by magnetism, discovering universal diamagnetism, a very weak repulsion from magnetic field. It's a property of everything, even stuff you don't think of as magnetic.
Which is important for things like magnetic levitation.
It's part of the basis for it, yes. And then, just 2 years later, 1847, something really forward-looking.
Go on.
He was working with extremely fine particles of gold colloids, and he noticed their color, their optical properties, were different from bulk gold metal.
Different colors depending on the size of the particles.
Exactly. This is now seen as basically the first observation of what we call quantum size effects. It's considered the birth of nanoscience.
Nanoscience in 1847, that's mind-blowing. He was decades, centuries ahead.
In many ways, yes. But what's also remarkable about Faraday is that he wasn't just locked away in his lab.
Right, he was a big communicator too, wasn't he?
Hugely passionate about it. He actually founded the Royal Institution's Friday evening discourses lectures for the public and the famous Christmas lectures for young people.
The Christmas lectures, they still happen today.
They do. He wanted to make science exciting and accessible. Thousands came to hear him, including famous people like Charles Dickens.
And didn't he write a book based on those lectures?
Yes, The Chemical History of a Candle.
Hmm?
Based on his Christmas lectures from 1860-61, it's still in print, translated into loads of languages. It's a classic of science communication.
He really believed in getting science out there.
Absolutely. He worked with journalists, editors. He saw science as part of culture, something everyone should have access to.
What drove that? Was it just belief in education or something more?
A lot of it stemmed from his deep personal faith. He was part of a small, devout Christian sect called the Sandemanians.
How did that influence him?
Well, for one, it gave him a strong ethical compass and maybe contributed to his humility. He famously turned down a knighthood,
He did. Why?
said he preferred to remain plain Mr. Faraday to the end. He also twice refused the presidency of the Royal Society, the highest scientific honor in Britain.
He wasn't interested in the titles and accolades?
Seemingly not.
Yeah.
And on a more serious ethical note, he refused to advise the British government on developing chemical weapons for the Crimean War.
Citing ethical reasons.
Yes. Despite his discoveries having potential military applications, he drew a line.
But he wasn't totally detached from public service, was he? Despite turning down honors?
Oh, not at all. He worked tirelessly on practical problems for the government and public bodies. He advised Trinity House for years on improving lighthouses crucial for maritime safety.
Okay.
He investigated deadly coal mine explosions, and was one of the first to really understand that coal dust itself was explosive, not just gas, a finding that was tragically ignored for a long time.
Wow. He also looked into pollution, didn't he?
Yes, industrial pollution,
Yeah.
air quality, even the famously disgusting state of the River Thames in London at the time. He applied his scientific mind to real-world public problems.
So a life dedicated to discovery, communication, and service.
That really sums it up. His legacy in public engagement is still honored today, actually. The Royal Society gives out the Michael Faraday Prize specifically to scientists who excel at communicating science.
And he was on the 20-pound note for a while too, right? A real testament to his impact.
Yep, quite the journey from that poor blacksmith's son.
So let's just recap. We've seen how this young man, starting with almost nothing, fueled by pure curiosity, became this absolute giant of science.
His discoveries really do form the bedrock of so much modern technology, motors, generators, our understanding of light, electrochemistry, even the start of nanoscience.
And it was all driven by this incredible self-discipline, persistence, this practical genius, but also guided by a really strong sense of ethics.
Definitely. A remarkable life.
And you mentioned his concern about public understanding. He
Mhm.
wasn't just about explaining science, he worried about people being easily fooled.
Right. He really did. He was quite concerned about public credulity. He actually spent time experimentally debunking things like table turning, a popular spiritualist fad back then.
He used experiments to show it wasn't spirits moving the tables.
Exactly. He also criticized the education system of his time, saying it didn't do enough to teach people how to think critically, to assess evidence for themselves.
That feels incredibly relevant today, doesn't it?
It really does. Which brings us to a final thought.
Okay.
Given Faraday's deep concern about critical thinking and, assessing information,
What would he make of our world now? With the internet, social media, just this constant flood of information and misinformation, what skill would Michael Faraday say is most vital for us to cultivate today to navigate these vast, often confusing fields of information all around us?